Is this antenna good or bad, and for which frequency is it useful? A question I'm often asked, because a lousy antenna reduces the range of a device considerably. Or another question, did the supplier cheat on this filter? At the end of this video, you will be able to answer these questions with confidence. And you know everything you always wanted to know about the Smith chart. For about $50. Is this a good deal? Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. If you use antennas or filters, your most important tool is a vector network analyzer, or VNA. It is essentially like a multimeter or an oscilloscope. But until recently, nearly nobody had one of those because its price tag started at around $10,000. With the appearance of these NanoVNAs, the price dropped to way below $50. The first generation had a limited frequency range. With the new version 2 generation's range of 3 GHz, such a device is a must for every advanced maker. Time to learn how to use it and how to avoid the most common mistakes. In this tutorial we will cover what is the difference between a VNA, a spectrum analyzer, and a VSWR meter. Which questions can be answered with a VNA? How does the VNA display its results and how to read them? Why is it important to know the limitations of the cheap VNAs and how can we overcome them? Why and where do we need to calibrate our instruments? And what happens if we do not do it? How is the quality of those devices? Do they provide correct information? Which additional software packages are available? First question, what is a VNA? It generates a signal and measures the amplitude and the phase of the signal coming from the device under test, or DUT. Simple. Other than the ohm meter, which only can measure resistance, it also can measure capacitance and inductance, because it also measures the phase between voltage and current. This is the main difference between a VNA and a spectrum analyzer with a tracking generator. Spectrum analyzers only measure amplitudes. But the spectrum analyzer can characterize external signals from transmitters. What problems can be solved with a VNA? Let's assume a simple system consisting of a transmitter, a cable, and an antenna that emits the power into the air. Of course, we want that all power is emitted. This happens if the transmitter's output impedance is well adapted to the cable's input impedance and the cable's output impedance to the antenna. Matched means they have the same impedance. Generally, this impedance is standardized to 50 or 75 ohms. For this video, I will concentrate on 50 ohms systems. If these impedances do not match, signals are reflected, do not reach the air, and heat the transmitter. In the old days, we had VSWR, or short SWR meters for that purpose. They measured the forward and the reflected power, as we see here. If there is no reflected power, the SWR is 1. If we want to know more, we use a VNA to measure the different parts' impedances and decide if the match is good or bad and what we have to do to change it. Cool. Unfortunately, a few errors can happen during this process, and we need a little theory to avoid them. How does a VNA work? It has one or two connectors called ports, or in the case of the NanoVNAs, channels. Let's first focus on port 1. This port emits a signal and, at the same time, measures the amplitude and the phase shift, short phase, for the reflected signal. If you know the amplitude and the phase of a signal, you can calculate the impedance of the device under test and show it on a screen. It is essential to know that these are the only measurements a VNA does on port 1. The rest is just displaying these results. For example, this VNA shows the impedance as well as the amplitude for a particular frequency. Nice. But most of the time we want to know the course of these values across a frequency range. This is why VNAs draw amplitude and phase curves across frequency ranges. On the NanoVNAs, the amplitude is called logarithmic magnitude or logmag, and the phase is called phase. The amplitude curve is more famous because it is used to determine the quality of a match. As we saw before with the SWR meter, the higher the amplitude of the reflected power compared to the forward power, the worse the match. Logmag and SWR show the very same thing, just for a different community, as we will later see. The main differences between an SWR meter and a VNA are: the VNA can measure and display also the phase of the signal. Because the VNA has a built-in transmitter, it can sweep frequencies and show curves. The SWR meter often is built for much higher forward power. So, a one-port VNA like this N1201A is sufficient to characterize antennas. Why does this NanoVNA have two ports? The second port is a receiving-only port. For filters, we are not only interested in the reflected power on port 1, we are more interested in the curve between the input and the output of the filter. And this is why we need this receiving port. The rest is the same. We can display amplitude and phase on port 2 the same way as on port 1. But here we see the measurements of the signal coming off the filter, not the reflected signal. By the way, the reflected signal is called S11 because the VNA transmits and receives the signal on port 1. The signal measured by port 2 is called S21 because it is transmitted by port 1 and measured by port 2. There are also S22 and S12, which can be measured by exchanging port 1 and port 2 on the NanoVNA. So far, we only dealt with simple curves across a frequency range. How does the VNA display impedances? It uses the Smith chart. This is a Smith chart. Scary. But it is handy and vital. Each point of the diagram represents an impedance. We go through the three most important points first. A pure 50 ohm resistance shows up right in the middle. This is the holy grail where we want to be. All shooters know precisely what I'm talking about. The next point is here. Nothing connected to port 1 or open. And a short circuit or short shows up here. You will use these 3 points over and over if you work with VNAs. All points on this line from the short via the 50 ohm to the open are purely resistive. I show you that in an example. I have a 500 ohm potentiometer connected to a NanoVNA. You see what happens if I change its resistance from 500 to 0 ohms. The point moves along the center line. Only in the end it turns away from the line. Why? Because the potentiometer also behaves like a coil and therefore has an inductance, which is added to the resistance. I did not know it, but the VNA detected it as a small phase shift between voltage and current. A sign that an inductance is in the play. Why do I know that this is an inductance? Because I know that above the center line we find all inductances. Below the line, by the way, we find all the capacitances. You do not believe it? Here I connect this beautiful variable capacitor I bought for my tube radio from video number 355. It starts nearly as an open, which is quite clear if we look at it. The plates are not connected and are far from each other. If I turn the capacitor, this capacitance gets bigger and we see the point moving along the outer circle below the center line. Unfortunately, I do not have a moving coil, but the same would happen with it just on the opposite side. Again, the measured values are the same as before: amplitude and phase. The VNA only shows more information. If we add a capacitor in parallel to the potentiometer, we can pull the point back to the center line. You see, we can use a capacitor to neutralize the inductance of the potentiometer. I do not need to care about the values, the VNA shows me and when I have to stop. Cool. But unfortunately, I cheated on you. I only used a frequency of around 10 MHz. If I change the range from 1 to 20 MHz, things become different. Suppose I leave the two parts where they were before, I get now a curve. Why is that? Capacitance and inductance change with frequency even if the part does not change. And this is what the VNA shows us without any effort. For example, we see that the curve crosses the middle line a second time at 1 MHz, in addition to the 10 MHz we saw before. And it nearly hits the short position at 20 MHz. So our potentiometer and capacitor behaves like a piece of copper at 20 MHz. Strange, but true. Now we can try to answer the question: would this be a good match if it were an antenna? Ask the shooters how much point they would get if they hit at those positions. The Smith chart is precisely the same. The distance to the sweet spot shows us the quality of the match. Here we would have the best match at 10 MHz with the closest distance to the 50 ohms sweet spot. As seen before, we can also check the quality of the match by looking at the SWR curve. It shows the distance to the sweet spot. And really, it is very flat up to about 15 MHz. Then it decreases rapidly because the distance gets bigger and bigger. At the sweet spot, the SWR would be 1. Now it is around 3, a bad match. You see, we do not need a Smith chart to just know if an antenna is good or bad. The SWR is sufficient for that purpose. When do we use the Smith chart? When we want to know how we can compensate for a bad match, for example, and for calibration, as we will later see. By the way, if you talk VSWR to an RF engineer, he immediately knows you are an amateur radio operator. He would never use this word. He uses return loss in dB, which is the same, just different. And of course, it sounds more professional. You can also display the return loss on a NanoVNA. It is the log mag from before. And it is around -6 dB at an SWR of 3. Now we have the basics to start working with a VNA. The most important thing you have to know is calibration. Never use an uncalibrated VNA. Never. It will show wrong values and fool you. There are two reasons for calibration. One, the VNA itself has lots of non-linearities. And two, the measurements heavily depend on where you attach the DUT. You probably ask yourself, why is it possible to drop prices from $10,000 to $50? Is the quality of these devices okay, or do they display crap? And here comes the calibration into play. Even if those cheap instruments are not accurate at all, you still can get good results. How is this possible? If we use well-known DUTs and tell the instrument their exact value, it can remember this fact. For example, if I attach an exact 50 ohms resistor to port 1 and tell the instrument that it is 50 ohms, it will later recognize a well-matched antenna and also display 50 ohms. So far, so good. But do we need to have a ton of resistors, capacitors and inductances to calibrate the instrument on all points of the Smith chart? Fortunately not. We only need 3. An open, a short and a 50 ohm load. If we calibrate even a cheap instrument at these 3 points, it will display all other points with acceptable precision. But do not forget, if we omit this calibration, These cheap instruments can show very wrong measurements. Also the professional ones, by the way. The calibration process is relatively easy. First, choose the frequency range you want for your calibration. This is very important because the NanoVNA invalidates a calibration as soon as you change the range. Then we go to the calibration menu and start with connecting the short to the VNA. After waiting for a short time, we can go on with the open and the load. This is called SOL calibration. If we connect both ports and tip through, we get a salt calibration. Now we can save it in one of the 7 memories. Here the instrument shows us if it is calibrated. Without this capital C, it is uncalibrated. You probably remember, I said you would see these 3 points over and over. Now you know why. We have to calibrate the instrument every time we change the frequency range. You might say, why not do a wideband calibration at the beginning? Then the instrument should know its calibrations at each frequency. Theoretically, this is true, and the N1201 SA does it like that. But those small devices only measure 101 or 201 points per scan. If you start at 1 MHz and end at 3 GHz, you get a calibration point each 30 MHz, which is more or less useless. Most antennas, for example, have a much smaller usable range than 30 MHz. By the way, if we switch the calibration off, we get very different and wrong results. We increased the precision of our device by factors using this simple calibration method. This is why you also have to order your VNA with a calibration set. According to Kurt Poulsen, a calibration specialist, the SMA calibration sets coming with the NanoVNA V2 are quite good up to 3 GHz, which is very astonishing. A professional calibration set can easily set you back $2,500 and more. This was the first reason for calibration. The second is the calibration plane. If we calibrate our instrument with a standard set, we establish a calibration plane right at the SMA connector. Maybe you ask yourself why we have a special open calibrator. Because there is a difference of a few millimeters between nothing and open, especially for higher frequencies. As soon as you add a cable or an adapter to your VNA, the calibration is no more accurate. Here is a simple example. This antenna only has a female connector, which does not match the female connector of the NanoVNA. I can solve this problem by adding this simple adapter. Look what happens if I add the adapter. The open point is shifted considerably because the signal travels to the newly established plane and back. Our instrument is no more calibrated. I have to calibrate my instrument at the newly established plane. But if I have no female calibration set? Fortunately, the NanoVNA can correct this error by using a port extension called electrical delay on the NanoVNAs. If I enter 165 picoseconds, the open is back where it should be. Good enough for us makers. If you do not trust me, you can visit Alan's W2AEW channel. He covers that and many other specialities of the NanoVNAs. The same but much worse applies if you want to measure on this demo kit, because you need a pigtail to connect the VNA to these tiny UFL connectors. Now we have 2 possibilities. Because the board has an open, a short and a load, you can calibrate on this board or use the port extension as before. Of course, with a much longer delay of 1.95 nanoseconds. Both establish a calibration plane at the end of this pigtail. Here are the results. With calibration on the board as well as with the port extension, the measurements are very similar. The result with the calibration plane at the SMA connector of the VNA is very different and wrong. With all this knowledge, we can answer our question from the beginning. Which antenna is better? They look very similar. Same manufacturer and same type. They should work on 144 to 148 and on 430 to 440 MHz. As shown before, I established the calibration plane on the adapter for frequencies between 100 and 500 MHz. For an overview, this is okay. I use 201 measuring points and get a space between the two measurements of 2 MHz. Enough to check if the antenna is terrible, but not enough to see if the antenna is good. Both antennas have 2 dips. Unfortunately, the dips of the fake one are not deep enough, so it is not usable for our purpose. If we look at the Smith chart, we see that its curve always is in the capacitive area. Maybe adding some inductivity would get a better response. The real one is far from an optimal antenna, but its dips at least are in the right place. We could now calibrate our VNA around 144 or around 430 MHz to get better measurements for the 2 ranges. But I think you got the point. As said in the beginning, we can also measure filters if we have a 2-port VNA. We connect port 1 to the input of the filter and its output to port 2 and measure S21. We have some filters on the demo kit to check the effect. But before we can do so, we have to calibrate the through. This is either done with such an adapter or, in the case of the demo kit, with this through. After establishing a salt with a calibration plane at the kit, and for the frequency range of 5 to 15 MHz, we see the expected dip at 6.5 MHz as well as the peak at 10.7 MHz for the other filter. Because the noise floor of this NanoVNA is around -75 dB, we cannot measure very good filters. Here we need a professional device with a noise floor below 100 dB. In my lab, the highest frequency I use is 2.45 GHz for Wi-Fi, and this will stay for the next years. I do not think that our gadgets will move to 5.8 GHz Wi-Fi soon. So now it is the time to invest in this new technology, if not already done. A few words about the available software. I use the VNA QT software for this video. You need it also for firmware upgrades. It is simple and does more or less the same thing as the firmware on the device. The NanoVNA Saver software is much more elaborated, but also has a steeper learning curve. You find the links in the description. Summarized, VNAs create a signal and measure impedances of DUTs like antennas or filters. They measure amplitude and phase to determine impedances. They display amplitudes, phases and impedances over a frequency range, either in XY charts or in a Smith chart. The Smith chart is made for systems analysis. SWR or return loss curves help for quick checks. To get the needed accuracy, VNAs have to be calibrated. Use a SOL calibration for 1-port antenna characterization and SOL-T calibration for 2-port filter measurements. For the NanoVNAs, the calibration range always is the same as the measuring range. Always establish the calibration plane where the measurement is planned, either by connecting the calibration set at this plane or by using port extension. The NanoVNA V2 is an ideal device because it covers all ham bands, the 433 and 868/915 MHz ISM bands and the 2.4 GHz Wi-Fi. All we need for $50. It has 2 ports and therefore can characterize antennas and filters. It is critical to know that it only measures a maximum of 201 points in the range. Only with a PC software you can extend this number. So it is necessary to adapt the frequency range to the questions you want to answer. For a quick antenna check, the full range up to 2.5 GHz is good enough. If you want to characterize a filter, you have to use smaller frequency ranges. The most important limitation is the small number of measuring and calibration points, with the effect that we have to calibrate the instrument way too often. its limited dynamic range does not show the quality of powerful filters. As always, you find the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.